Good day, my dear fellow mathematicians. In today's scenario, we're going to discuss all about the development of mathematics in modern period based on non-Euclidean geometries. But before of that, we're going to target the learning objectives within this discussion. Firstly, we're going to discuss the origin of non-Euclidean geometries. Second, identify the personalities associated with non-Euclidean geometries. And the last is present a timeline of these geometries from the line of their conception. So what is geometry? Geometry is a branch of mathematics that concerns the properties of space such as shapes, size, distance, and area of that within surface. What about Euclidean geometry? Euclidean geometry is named after by Greek mathematician Euclid. And also, it is a kind of system of studying flats and three-dimensional shapes within axioms and postulates that have been established.
Problem of Euclid's fifth postulate. The parallel postulate goes centuries of debate, complex compared to other postulates. Mathematicians try to prove it from other old fields. The problem of Euclid's fifth postulate, a historical and mathematical puzzle. Euclid's fifth postulate, also known as the parallel postulate, has puzzled mathematicians for over 2,000 years. Unlike his other postulates, which are simple and intuitive, like a straight line can be drawn between any 2 points, the fifth postulate is far more complex and less self-evident. Independence of the parallel postulate. The fifth postulate is independent of others, changing it creates new geometries. Independence of the parallel postulate, a turning point in geometry. For over 2,000 years, mathematicians believed Euclid's fifth postulate, the parallel postulate, was too complex to be a truth-stating assumption. They tried to prove it from Euclid's other simpler postulates, but all attempts failed. Eventually, mathematicians discovered something groundbreaking. Early attempts to solve it. Proclus 5th century AD noted failed proof. Zachary 1733 assumed postulate false. Lambert 1766 found triangles 180 degrees Celsius. Early attempts to solve Euclid's fifth postulate. For centuries, mathematicians were puzzled by Euclid's fifth postulate, so called parallel postulate, because it was so much more complicated than that other postulate. Many believed it wasn't really fundamental and could be proven by the other. This led to many early attempts, and although they failed to prove the postulate, they made important discoveries.
Good day everyone. Today I'll be talking about the birth of non-Euclidean geometry. This was a major breakthrough in mathematics during 19th century. It introduced a new way of understanding geometry beyond Euclid's traditional ideas. The main founders were Nikolai Lobachevsky and Janos Bolyai, while Carl Gauss supported the theory but never published his work. Nikolai Lobachevsky was a Russian mathematician known as one of the founders on non-Euclidean geometry in 1829. He published Foundations of Geometry, where he introduced hyperbolic geometry. In this geometry, the sum of the angles of a triangle is always less than 180 degrees, a key difference from Euclidean geometry. Janos Bolyai, a Hungarian mathematician, developed similar ideas independently. He published his findings in 1832 as an appendix confirming results close to Lobachevsky. Together, their works prove that alternative geometries could exist, opening the path to modern mathematics and even Einstein's theory of relativity.
This is Carl Friedrich Gauss. He was born in 1777 and and died in 1855. A highly influential 19th century German mathematician, astronomer, geodesist, and physicist, often called the Prince of Mathematics. And he also credited the first proof of fundamental theorem of algebra. Are the two main types of non-Euclidean geometry. We have the hyperbolic geometry and elliptic geometry. Hyperbolic geometry, two parallel lines are taken to converge in one direction and diverge in the other. And the last one is elliptic geometry. Elliptic geometry in which Euclid's parallel postulate does not hold. Instead, as in spherical geometry, there are no parallel lines, since any two lines must intersect. Riemann's contribution 1854. Riemann's contribution was a paradigm shift in geometry, providing a foundation for understanding curved space and influencing the development of modern physics.
So here are the timeline of major and milestones. So first is Saccheri. In 1733, he was an Italian Jesuit who did an important early work on non-Euclidean geometry. So he aimed for his work is to study the definition Saccheri distinguished. So the first he calls definitions or reals. Example, we could define the mild point of a line segment as the point in which divide the segment into two equal segments. So the second one is Lobachevsky. So he first published his ground-breaking ideas on the non-Euclidean geometry in 1829. So in 1829, he published a concise outline of the foundations of geometry, the first account of non-Euclidean geometry to appear in print. The third one is Boyle's Appendix in 1832. In 1882, the appendix laid out the foundation of a non-Euclidean geometry by postulating that through a point, not a given line. Riemann's lecture in 1854 held his first lectures in 1854, which founded the field of Riemannian geometry, and thereby set the stage of Albert Einstein. In 1868, Beltramy's model, it represents the hyperbolic geometry by mapping points to the interior. For Einstein, relatively, the theory of relative include the special theory in 1905 and general theory in 1915, which redefines space, time, energy, and gravity. The real-world applications in Einstein's generally relatively in 1915, it described curved space and time. It refers to the concept of Einstein's theory of general relativity that gravity is not a force. So in use in GPS, astronomy, and physics, in GPS, the clock satellites in orbit run faster than clock on Earth. For the astronomy, it is used to understand the phenomena, and the physics, it provides the theoretical, it provides the framework understanding the universe.
Why it matters to study non-Euclidean geometry? Studying non-Euclidean geometry helps us understand how mathematics developed beyond the limits of Euclid's traditional ideas. It shows how questioning can lead to new discoveries. This branch of geometry broke the ideas that there is only one kind of space and opened doors to modern science, especially in physics, astronomy, and even technology like GPS. It teaches critical thinking, creativity, and the importance of exploring different perspectives in solving problems. To summarize, non-Euclidean geometry emerged in the 19th century when mathematicians like Gauss, Lobachevsky, and Bolyai challenged Euclid's fifth postulate. They discovered new types of geometry, which are the hyperbolic geometry, where many lines can pass through a point parallel to another line. Next is the elliptic geometry, where no parallel line exists. These ideas revolutionized how people viewed space and shape, paving the way for Einstein's theory of relativity and influencing mathematical thought.